Hey, Dr. B here, and let's determine the shape of binary molecules. This oftentimes goes by the name of vsepr, otherwise known as valence shell electron pair repulsion theory, which is an exercise in confusion. Let's just call it how to figure out shape. First of all, if we're sticking together substances, especially organic ones, the shape falls out rather simply from using some simple honk rules. Hydrogen forms one bond, oxygen 2, nitrogen 3, carbon 4. The halogens, represented as X, meaning fluorine, chlorine, bromine, and iodine, also typically 1, although there are some exceptions, which we will see in this example. So if you throw them together and you get substances like carbon dioxide, there you go, it's going to be linear. Carbon tetrachloride, 4 things arranged around a central atom, trying to spread out as much as possible will give you a tetrahedral shape. If you've got a double bond around carbon, just one of them, it's going to bend it into a 120-degree bent angle. So we can come up with shape pretty reasonably without doing anything fancy. However, once you get into substances like this, and by the way, a lot of these are a bit odd, right? Look at these, like got noble gases bonding. We've got things forming 6 bonds, not something you see very often. There is a systematic way of coming up with its shape, and we're going to go over it here. What you can do is just add up the total number of valence electrons and see if you need any lone pairs. You compare it to the simple valence electrons they should have, and if it has extras, we throw them on the central atom, and from there the shape comes out. Much better taught by example, so let's dive in. It's very likely after you do a few of these, you'll see the pattern and you can come up with a shape for just about anything. We'll also show another slide where we go over the systematic pattern for where the shapes come from. I'm just going to throw them at you here, and I hope that's all right. Silicon, pentafluoride, anion. Well, always draw the central atom, throw the 5 things around it, and see where those electrons go. There's silicon, there's the 5 things around it. But now let's see if the electrons work out okay. Silicon's supposed to have 4 valence electrons. Each halogen, if you see the periodic table, has 5. That's 5 times 7 is 35, plus the 4 is 39. It does have a negative charge, so it's supposed to have 80 electrons. When you draw this thing out, you only get the 39. Add them up, and I think you'll see it's true. Don't forget a bond counts as 2 electrons. So throw 1 extra electron around this thing that would be just resonance delocalized, and that would be our 40 electrons. We're going to call this shape, and don't worry about this too much now, but maybe you already know it. This is a trigonal bipyramid, 5 things around a central atom. I think we're going to get the same shape from this because draw your phosphorus, draw 5 things around it. It certainly looks like a trigonal bipyramid just like the other one, but make sure the electrons make sense. If we do that, we'll have 40 electrons. And do we? Well, 35 plus the 5, this is right under nitrogen, does make 40, so add them up and we're good. 8, 16, 24, 32, 40, trigonal bipyramid. No lone pairs, no charge, everything's clean. Sulfur tetrafluoride, I draw the sulfur, I'd put the 4 fluorines around, but it looks like we needed an extra lone pair. Does that make sense? Well, sulfur has 6 valence electrons, each fluorine has 4, so that's 28 plus 6, that's 34. So when we normally draw it, imagine that thing is gone, 8, 16, 24, 32, but clearly this has 34. Put the lone pair on the central atom. This will change its shape because it's no longer a trigonal bipyramid. There's no fluorine or anything there. It's just taking up space. We call this a seesaw shape. Chlorine trifluoride. Well, chlorine is acting strangely, is it not? But it has available d electrons, so it can do these weird things once in a while. Draw the chlorine in the center, 3 fluorines around it, and see if you need any lone pairs. Every one of these is 7, so it's 28. And if you add them up, you're only going to get 24. We have 4 extra electrons to account for. Throw them on the central atom. So it looks like a trigonal bipyramid, but these are just nothing. They're just space occupiers. This is called T-shaped. Xenon Tetrafluoride. Write the xenon, make it look like it's linear, but is it? Let's find out. This is 8 plus 2 times 7, that's 22. Well, normally we'd only have 16. We got 6 extra electrons. Throw them all around the central atom. Look at that. It's a pretty rare one. And it is still linear because all 3 of those are just taking up space. Silicon hexafluoride dianion 4 plus 6 times 7. That's too many, right? 6 times 7, well, 5 times 7 is 35. 42 plus the 4, I get 46. This is really pushing. 46 plus 2 makes 48. So 8 times 6 does equal 48. I think that we're going to be fine with no lone pairs at all. I did my math right. Yeah, and so there you are. And so this is all 6 occupied. Throw those extra electrons in the form of a negative charge, right? We didn't have to add any lone pairs. We were fine. And that is octahedral. Phosphorus hexafluoride with a negative charge. Well, here we got the 6 times 7 is 42 plus 5 is 47. Oh, one more makes 48. 8 times 6 is 48. Another clean octahedron. Okay, try these on your own. I'll do each one so you can follow my math, but I hope you're seeing the pattern. You can do this yourself. This is 6 plus 42 is 48. It's nice, clean, no charges at all. This is just like all halogens. Draw the bromine, 5 fluorines around it. Let's see if we need any lone pairs. And that's 6 times 7 is 42. 8, 16, 40. We have 2 extra electrons. So I think you're going to have to put one pair of electrons on bromine. And there it is. Not a very common shape. We are going to call that a square pyramid. And finally, xenon tetrafluoride. I already showed the answer. Let's see if it makes sense. Well, we threw all 4 on, but we're wondering if the electron count is reasonable, and in fact it's not, because it's 8 plus 4 times 7 is 28. That's not 32. That is not 34. That's 36. And so we need 2 lone pairs. You put them on the central atom above and below, and this looks like a square planar structure. That is valence shell electron pair repulsion theory. We're going to do one more slide on it just to really bring it home.